So I suggest we go to the next speaker, and the next speaker is Arnold Mulder. Arnold Mulder holds an MSc degree in Environmental Science and Technology from Wageningen University, and at present he works as a private consultant at Amecon Environmental Consultancy, and before that period, more than 30 years experience in big companies, TNO, Biothane, and also Gisbrocade, so a very experienced presenter. The floor is yours.
Yes, Jan-Peter, thank you for your introduction. Ladies and gentlemen, I should like to tell you something about a research project we have carried out about sustainable treatment of anaerobic pre-treated potato wastewater for the sustainable removal of nitrogen. So I want to discuss with you the next topics in the next 20 minutes. First, I want to introduce you in the need, why we do need to nitrogen recycle and why we have to do that in a sustainable way. Then I will tell you, it will surprise you a little bit about Anammox. Then I will explain you a little bit about the experiments we did with a combination of an MBBR reactor and a Demox reactor, a little bit variation of the current technologies, and I will show you some results. First, I want to show you the nitrogen cycle, how this is interfered by mankind. I want you not to explain it at all, but it's rather important to realize how men extremely influence this cycle, because you all know, of course, you start with nitrogen, which is in the air, and in the past it was only biological nitrogen fixation which brought us to vegetable protein, and from vegetable protein, of course, cows and also men can live. But in the last year we eat much more meat, and the meat is coming across to cows, and this resulted in an enormous increase of ammonium in our wastewaters. This can really be observed that it is increasing because we eat more meat, and we should change this. But you can the discussions follow every day in the newspapers. But that is one thing. The other thing which is important is to realize the Haber-Bosch process, the amount of nitrogen fertilizer which is fixed by mankind, and I can show you that in the next slide, because this process was started in the beginning of the 20th century, and this is the process. Haber-Bosch, they discovered it during the First World War, and they combined methane with nitrogen gas, and they make fertilizer. It was used, of course, for making ammunition. But when you look to the application of this process, it only consider, when you look to it in the time, the amount of fertilizer produced, and you look back, that the start of the process in the early 20s in the last century, it lasts until the 60 years of the last century, because this started to increase. Here you see the time. Here you see the megatons of nitrogen which is produced by the fertilizer globally, worldwide. If you think it has something to do with the increase of the population growth, that's not true, because the population growth in those years only doubled, and this was tenfold. You can also see that if you express this in the amount of nitrogen fertilizer globally produced per capita, you see this increase from the 60s to till nowadays is about 16 kg of nitrogen per capita. So this shows you that it's important that we are overloaded with nitrogen. And all the discussion about greenhouse gases has something to do with that, of course, because this nitrogen is introduced in the environment somewhere. Part of it, of course, in the wastewater. That is this slide showing you. This is showing again the figure. If you have a globally mass balance about nitrogen, globally 10 kg about per capita, and in the sewer system you find back this amount. If you do it, for instance, for 2 Western world countries, you see the amount of nitrogen fertilizer used is even higher in Norway and the Netherlands, but the same amount, or might be higher, in what you find back in the sewer system. So this shows you that's important to do something with. That is really a problem. We have to deal with that. Yes, then I come back because I want a little bit to show you about the Anammox process, because it was a serendipity of some site research which was done in all type of denitrification process. There it was suddenly discovered that when you start with nitrate, it was reduced until nitrite in a column which is in denitrifying conditions, and then it showed out that there was a removal under anoxic conditions where ammonium was removed, and later it appeared at Technical University of Delft that this was a combination of ammonium combined with nitrite and producing nitrogen gas. Now everybody knows this under the name of Anammox nowadays, and you can make this nitrite in two ways. Of course, you can start with ammonia, partly oxidize it, but you can also use, of course, nitrate and partially denitrify it into nitrite. That's the other options you can follow. Now, this started all in 1986, and since then, the nitrogen cycle has a lot of new reactions. Here I made an overview for you, just to consider, because there are a lot of discussions how many energy we can gain when we are using Anammox processes. Here I decided theoretical values, because in practice it's difficult to cover this all. You'll see, when you have conventional nitrification, costs you 1 kg of nitrogen costs you 4.7 kg of oxygen. With nitrification, if you partly nitrify and then denitrify, you can also use, of course, the new process which was recently discussed. You can also, it costs you that amount of oxygen, and you can, of course, autotrophic nitrogen removal. And then you see this suddenly this decreases the amount of oxygen. So the difference between the previous talk and in this peak, there is still some oxygen. You see, this is the gain you can make then. I also added this one. This, of course, for sun-rich surroundings might be interesting to have a phototrophic nitrogen removal, because it costs you not any oxygen even. It produces oxygen and consumes, of course, carbon dioxide, but that's another story. Now I want to show you a rather complicated graph, but this is showing you the energy in the whole nitrogen cycle. If you start here, if you have conventional nitrogen fixation and nitrogen removal, then you have, of course, the 45 kg for the Haber-Bosch process, because in the y-axis the different processes, the different cycles are standing. And here the energy used in megajoule per kg of N. And what's interesting and surprising is that you have, of course, the basic is in all the equal. You have to, if you go for all those processes, you are going to nitrogen gas again, and you need to fix the nitrogen from the air and then make fertilizer out of it. Then if you have done that, you have to treat your wastewater, and it will cost you oxygen. And that oxygen amount for nitrification, traditional nitrification, is this figure, the brown one. If you go then for this one, you have here the nitrogen removal via nitrite. You give you a small reduction of aeration cost, of aeration energy. If you go to Anammox, it's still decreasing, it's still half of that. Because you don't have to oxidize all the ammonium, but only half of that, and you have only partially to oxidize it. But the majority of the gain, if you go to Anammox process, is the use of a COD, which you're using for denitrification. Because if you use methanol, to going back from nitrate to nitrogen gas, costing you an enormous amount of energy. If you go through nitrite, this is reduced, and if you have only the Anammox process, so this is the really gain from Anammox process, is that you don't need a carbon source for denitrification. You see that is the majority of the energetic gain you are making. That is really surprising, and oxygen is also important, but not that much. And then, of course, you have the discussions about, do we have to go to urine recycling, etc. Did you say we must go that way? I did make here the assumption, if you can do that, you cannot do that everywhere, because the transportation costs are that high that most likely it will be in the future the most effective way to get a sustainable removal of nitrogen. So this was a long introduction, and then I made here again for you the exact processes. This is conventional, everybody knows most likely here, the partly nitrification for the making nitrite. This is the second stage, a lot discussed already. Here you see the amount of methanol costing for you for the conventional denitrification. The Anammox process, and for the next for the last half of my time, you need to keep this in mind. You need 1.32 nitrite for making this ammonia, because this ratio will come back later. And this is done a Demox process, because I want to discuss because a lot of Anammox processes, the majority will produce the tried from the aerobic part. What we have investigated for the potato starch wastewater is, for the potato chips wastewater, is to use also nitrate. To use nitrate, combine that with acetate, and then make nitrite out of that. And then you get this type of reaction, and you see that with this one you need less NOx components, and that will be shown later on. Yes, I think I skipped this in view of the time, but you see there are a lot of variants from Anammox processes you can find in the literature. You see they have all different type of names. It is called, the original one was Anammox, Oland, Sharon Anammox. You can go on, and the important one is of course the conversion capacity. That is interesting. Parks have found big ones with high conversion. Or is that in the next slide? You see nowadays the majority can reach capacities of around 1 to 3 kg of nitrogen per cubic meter per day. These are really high conversion rates. You see here one again. So the Canon system, so a lot of processes, also the Demon process we have to mention, which is applied by the Grondmeijer, I believe, in the Netherlands. So there are a lot of examples in that. So, but we, so I think you can say Anammox process is a promising process with a lot of interest. But yield and growth rates are relatively low. The process is inhibited by oxygen, also nitrite may be inhibitory, and sulfite is inhibitory. So there are also a lot of drawbacks which make the process sensitive. And suspended solids will result in the washout of the sludge. So many reasons to think about it, because we were confronted a couple of years ago with the effluent of a potato chips factory in Broek op Langedijk, where we have contact with them. And now you can look also to the nitrogen balance of this factory. If you look to 1 ton of potatoes, majority is coming into the chips, for instance, but part of the nitrogen which is in here is ending up in the wastewater. So in this wastewater they have a nitrogen problem, but in Broek op Langedijk they're standing a factory where they are now have an anaerobic pre-treatment, and after that a carousel where they aerobically nitrifying this wastewater effluent into nitrate. Now, what was interesting for our process, we were interested to apply this type of pilot plant, and that we have researched for 2 years, where we started with the USB. It was a full scale existing. This is all existing, but we take a flow out of this one and we put that in an MBBR, which is nitrifying system. Afterwards, the effluent came to an EGSB reactor where we want to make granules to do the Anammox process. And there was a bypass which was fed to that system just to apply and to remove also the nitrate, because as you have seen in the Anammox process, part of the nitrogen which is produced is all ending up in nitrate, and that might be sometimes a drawback. So this is the pilot plant we have investigated. You have two steps. This is an EGSB reactor, which is standing 7 meters high, and besides that there's an MBBR system which is aerobic, and so the wastewater is entering first into this one and fed into the EGSB, and part is directly fed into this one. So here you see we have a blower and a separation system, and we have some chips where the nitrifying biomass was growing on. So this is a close-up, but you see we have used this type of disc to concentrate the nitrifying biomass. Now this is some details of the reactor. Both reactors has a volume of about 1.5 cubic meter and 2 cubic meters. The HSB was a little bit higher, and the hydraulic retention time was in the first reactor was 7 to 8 hours, and in the big one was 3 to 4 hours. This is the effluent composition of the effluent of the USB. And here you see the total series after anaerobic pre-treatment of this wastewater is around 1,000. There is a lot of soluble, because the total, here you see a big difference between the total COD and the soluble COD. That was, yes, that was the how do you say, the triggering factor. Can you indeed apply Anammox systems with so much suspended solids? That was the trigger to do this process. There is some suspended solids, an ammonium concentration of about 200. If it varies also a little bit. What varies also is the soluble COD, therefore we run into some problems, will be shown later. You see, on an average, the biodegradable COD is around 100 milligram per liter, but you see it varies considerably, and that gives us some troubles, as will be shown in the next slide. First, I want to show you some results of the nitritification, the first step. This is the MBBR. There are a lot of information on this slide, but what is relevant to see is the above one is the ammonium which is coming in. So that is the ammonium in the effluent of the USB, the anaerobic full-scale reactor. And you see what is then relevant to you is the ammonium concentration. You see it is, yeah, for 80% the ammonium is converted into nitrite. That are the other ones. You can see that the green and then the other ones is not so important. What's important is you see you succeeded in running this for 1.5 years, that you hardly get any nitrate production, because there's always a discussion. People say you cannot operate it like this, but if you keep it under oxygen limiting conditions, you see it's possible to run it in this way. This is just to show the conversion capacities. Just to show that after startup, the process starts up within a month. You'll see ultimately you reach a conversion capacity of about nearly 1 kg of nitrogen per cubic meter per day, and most likely it's oxygen limited, that you can even go higher, but we didn't try that. What is also relevant is this is the nitrogen balance, because always you are interested, are you not producing a lot of N2O, etc. So we make a nitrogen balance of the ammonium coming in and the nitrate coming out, and you see we have some problems with the mixing in such a system, because that's of course relevant if you have such a carrier. It must be mixed well, because we discovered that after the startup, the carriers will become heavier, of course, and then so the mixing was incomplete in this period. So we changed the process of mixing, because you have two blower, you have coarse aeration, and if you take one on one side, you get a better mixing of your carrier material. You can also control that, but that was so we improved that, and you see that after that period, because the red ones, that is the gap in your nitrogen balance. So here we have partly denitrification, and that might have been also, of course, N2O gas, but I'm not sure about it. But you see afterwards, the nitrogen balance is even rather fixing rather good. Sometimes you also be low, so you can see he's closing down. Here is the nitrogen loading rate against the nitrogen conversion rate, and you see also these data show that the process performed rather well. Here we also did some measurements, of course, with our carrier, and you see that the process is really oxygen limited. If you increase the amount of oxygen, you see you can reach enormous conversion processes which is carrier-based in this carrier-based system. Now then we come to the Deamox reactor. This is a little bit more confusing, of course, but we again here it's important ammonium coming in. That is the above one. This is the dotted dots are that, and the ammonium coming and the nitrite coming in the influent are those ones. And of course here is relevant the ammonium in the effluent, and that are these ones. And you see that we succeeded indeed in getting here some Anammox activity. And the red ones is when you get nitrite in your effluent, and that's not what should be, because then the process is not running well. So we have had some problems. Here, this is the winter period. We have some problems. 3 minutes. I will go some fasten it up. But you see, when it is too cold, the process runs into problems. Later, we have some problems with overloading by COD, and so that are the drawbacks of this system. That is sensitive for some things. So temperature is dangerous. You must not become the temperature below 25 degrees, and the COD load must not be too high, because then you are consuming nitrite with and the nitrite is consumed by the COD, so you get running into problems then. Let's go on. So this is the nitrogen balance. You can see because we measured also the gas production, and you see that the gas production, because the blue one and the red one, that are the nitrogen production and nitrogen conversion, and they are fitting rather well, so your balance is fitting. This is the loading rates in this reactor. You see ultimately we have the loading was into 1.6 kg of nitrogen per cubic meter per day, and the conversion was somewhat lower. That was here. But you see here we have run into some problems as told by temperature and by COD loading. Yes, this is a little bit too far, but here is the development of the ratio. I discussed with you that the ratio, of course, is always interesting in this type of systems, the nitrite consumption over the ammonium consumption. And you see for the original Anammox you have a factor of 1.3. And you see here we are a little bit higher due to, of course, part of the nitrite will be consumed for the COD oxidation. If you put it in this way, you see get another relation. Because you can also express it, of course, ammonium removal and nitrite consumed, and then you get a relation which is somewhat lower. Both systems most are like true. Here, this is also difficult, but here I want to show you the effect of soluble removed. I did not apply the Dietrich-Stapel method, so I put all my results here in these figures. But what's important is that if the COD is too high, and so as well as in the MBBR, the MBBR can better perform against some COD, but if the COD is too high, then the conversion is reduced, because this is efficiency. And here you have also the soluble COD versus the removal efficiency. And especially in the Anammox and Deamox reactor, you see that when you have above, after dilution, too high soluble COD removed, the removal efficiency is affected. So that you should keep that low. This is the profile in your anaerobic reactor. You see clearly that when the amount of ammonium removed in your reactor, this is the height of your reactor, and this is the amount of NOx. And you see clearly that the nitrite is going down, also ammonium is going down. It started here at the bottom of the reactor, and you see that some nitrite is produced, showing that Anammox activity is really the basis for the process. These are the granules looking like, say a little bit reddish, but not so reddish as the figures sometimes others are doing. But you see this, and if you do some activity measurements, you see the same type of processes. Clearly nitrite and ammonia going down, gas produced, and nitrite also produced. Now, this is the same type of figure. I can skip this for the time. This is an interesting one. This is the Deamox activity, because, as I told you, one of the reasons to do this research is to show that you can also go with nitrite and using nitrite. Here we have added nitrite, ammonia, and acetate, and you see ammonium is nitrite is consumed, acetate is decreasing, but also the ammonia is decreasing. If you do it again, you see acetate is rather going down, but also ammonium and nitrate are going down. That shows you that you can indeed use nitrate for the Anammox process, for removal of your ammonium and anoxic conditions. Now, this is the summary of the results. The summary is showing you that we kept successful this tandem of MBBR and a Deamox reactor. It's successful at conversion loading rates of about 1 kg, and then the conversion in the MBBR of about 80 to 90% nitrogen. The nitrogen process produced mainly nitrite and only 5 milligrams of nitrate. In the Deamox reactor is the same. You can reach a loading of about these values, and also here you get only a small amount of nitrate. This is in the last slides. You see, you would, with normal Anammox, you would expect it under those conditions 25 milligrams of nitrate produced. Under those conditions, it was only 5 milligrams. So we succeeded indeed in our goal to reduce the amount of nitrate in effluent. However, the process appeared to be sensitive for two things. That is temperature below 25 degrees. And also if the COD values, the biodegradable COD values in your effluent of USB, fatty acids and so is too high, then you can run into problems. I thank you for, and also, the last one, of course, the process is not affected negatively by suspended solids concentration around 1.5 to 1 grams of total solids. So, I thank you for your attention.
Okay, Arnold,
yeah.
Thanks for your presentation.
Yeah.